Hi, my name is Keith Wilbourn. I'm a consultant working on cannabis packaging in these days. I work mainly through Red Copper Consulting, which is my consulting company, and I'm also a senior associate at Montesino Associates. Next generation plastics for cannabis packaging can take a lot of different forms. Most of us are very familiar with the polyethylenes and the polypropylenes of the world that are out there, and that's the vast majority of what you see in packaging, not only cannabis packaging, but food packaging, some industrial packaging as well. But we want to talk about cannabis packaging in particular today, and I'm going to talk about more of the newer biodegradable and compostable packaging materials that are available out there. Cannabis packaging really should fit all of the following criteria. The first thing is that it needs to keep the product safe and maintain its efficacy. That is, it needs to be effective in keeping the product as it was meant to be when it's sold. The second is to comply with all the applicable regulations for the packaging materials, and this is going to vary on a state-by-state basis. We also would like it to maintain effective branding for the manufacturer or the distributor, whoever happens to be maintaining the brand for that particular material. It also needs to be well labeled. The consumers need to understand exactly what they're getting into, especially with cannabis, and the implications of consumption. And then the last one that I want to talk about there is sustainability. Be sustainable as much as possible. Many of us have seen the litter that's out there, the polyethylene bags, the small tubes associated with regular packaging materials, and these really have no lifetime within our degradation in our lifetime. That lifetime is going to be along the lines of between 500 and 1,000 years, depending upon the material. So let's talk about recycling of those conventional materials first, because that is still a possibility for all of this. The major materials in the plastics field, the polyethylene and the polypropylene, all of this that we're going to talk about is fossil fuel based. So the polyethylene and the polypropylene, that is low density, linear low density, high density, regular polypropylene. Very little of this is actually recycled because there's no good way to separate the types. Of these polyolefins is what we refer to these as. At best, about 5% is recycled, and most of that is high density polyethylene. Think milk jugs and things along those lines, but realistically, most high density polyethylene does not get recycled. You cannot easily recycle the linear low density and the polypropylene material because there is not a good stream for use of that particular material. Polyethylene terephthalate, on the other hand, that is much better than polyethylene. And if you think about Coke bottles, Gatorade bottles, things along those lines, it's still much better than polyethylene, but still only 30% is recycled, meaning 70% is not recycled. It creates a much cleaner feedstock than polyolefin materials. There's a lot of others that cannot be easily recycled. That is polystyrene, think styrofoam, polyamide, which is another word for nylon. And there's a lot of mixed materials out there. People mix these materials together to create specific properties for the packaging materials. For example, if you need to have something that has a high barrier to it, you might have other things mixed in with it that keep oxygen and moisture out of the package, or things that things that promote puncture resistance, things along those lines. So what can be done with all those conventional plastics? We can continue with the polyester in the vein it's going now. There are some states already that require us to recycle these, that you can recycle for a fee, whether it's a nickel or a dime or whatever it happens to be. But there's other ways to do it too. And the first one that I'd like to take just a second about is chemical recycling. And what chemical recycling is where you actually take the polymers down to their base components. That is, if you had polyethylene, for example, it will unzip the polyethylene molecules and take it back to ethylene. The ethylene can then be reused. So another of these is doing energy extraction, and that's a fancy term for burning the material, pyrolysis of the plastics, to extract the energy. And you're basically burning to create energy and carbon dioxide. To do this, obviously the CO2 is a greenhouse gas, so we don't really, unless the CO2 is captured and sequestered in some way, shape, or form, that's not the best of the options. Reuse is another that's I haven't listed here, but the fact of the matter is that most people, they either don't understand recycling or they don't care. So you see a lot of the materials go into landfills. You see waste by the side of the road. There's a lot of things that are undesirable about a lot of the plastics that are out there already. So we go on to the next slide, and what we're going to talk about is the possibility of biodegradable packaging. Biodegradable materials might degrade under the right conditions, but a lot of the landfills that are out there don't really fulfill these needs. Most landfills in the US are what are called dry tomb landfills, and they're built the way that they are to prevent groundwater contamination. These materials are kept dry for the most part, and because of that, they don't degrade. There needs to be some moisture content for these to degrade. Dry tomb landfills are engineered the way that they are to keep the groundwater in neighboring areas clean, and this really does not help with biodegradation. Some of the biodegradable plastics that are out there, the most commonly known one is polylactic acid. It was first used on a large commercial scale for sun chip bags back in 2004, 2005, 2006 timeframe. And it was eventually scrapped because the package was loud, meaning if you're trying to eat a bag of sun chips in your class, it was very disturbing to the people around you. The biggest issue with those types of materials at this point is that there's very little infrastructure for biodegradation or composting. There are some places in the US that have commercial composting out there that do take packaging materials along these lines, but most do not. So let's talk about the different types of plastics that are out there. There are three major types that I want to talk about here. There are synthetic plastics, biopolymers, and bioplastics. So synthetic plastics are the first ones that I talked about, the polyolefins, and they're usually made from fossil fuels like ethylene and propylene, and those are obviously commonly found as part of oil. Biopolymers are typically biologically active polymers, and they're made from sustainable resources and generally have naturally occurring repeating units in them. Bioplastics are polymers that are made from renewable sources and are generally biodegradable or compostable. The one thing that you'll see as we go through the talk is that these three types of materials are not necessarily mutually exclusive of one another. Let's talk about bioplastics from sustainable sources. There are other biopolymers that are out there, and they have been made since the early generations of polylactic acid. But we're going to concentrate on PLA for a moment here. PLA is difficult to process. It's brittle in its unmodified form and does not revert back to its constituent materials quickly. New materials were necessary for biodegradation, which then brings us to the composting end of all of this. If you look at the picture that's in the slide here, that's an industrial composting facility close to Charleston, South Carolina. And there are some peculiarities associated with industrial composting versus what you do in your backyard. Backyard composting is usually done at lower temperatures. And for things like PLA, it would take it a very long time to degrade in your backyard. If it goes to an industrial composting facility, the composting is done at much higher temperatures, and the content are monitored so that they make sure that the breakdown occurs in the most efficient way possible. One thing to remember is that compostable material is biodegradable, but biodegradable material is not always compostable. So, with regards to composting, composting involves the mixing of decaying organic substances, and it's used for replenishing nutrients and organic matter in the soil. It's the stuff that you put on your vegetable garden. It's the stuff you put on your flower bed after the composting has been completed. Most composting in the US is done with yard waste. So if you see a composting facility listed in locally, more than likely they will take yard waste, but a lot of them don't take food scraps just yet. If you go to some of the places, for example, in some parts of the country, you'll see that the composting has progressed a little bit faster. And so with regards to that, what I'm talking about is that the composting facilities do in some very small parts of the country accept biodegradable packaging materials and also the compostable food scraps. So you're gonna see more and more in the future where composting is done with food scraps. If you go to Europe, you'll see that this is a very common practice over there. Biodegradation of both packaging materials and food scraps together have created a much more friendly environment for these materials. One of the things to take a look at here are the insignias that I'm showing there on the left-hand side of the screen. The certification, the TUV certification, there are 3 there. The first ones that I'm going to concentrate on are the home and industrial composting of materials. They're on the very left-hand side of the screen. So home composting are some of the more easily composted materials, and we'll talk about those in just a minute, which ones are more easily composted. And then there is industrial composting, and these insignias are on a lot of the packaging materials that you'll see, particularly in Europe, but it's becoming more common over here as well. There's another there, the Bpi Compostable, and the Bpi is an organization here in the States that certifies materials. And you see there, it says ASTM 6400. That's a testing regimen to ensure that materials are indeed compostable. You also see on the far right-hand side of those, the compostable, the EN 13432, and that's, again, another compostable certification that is available in Europe. So the thing about all of these different composting certifications is they all have their own way of making the doing the certification. So there are some standards across each of these, but the methods under which the tests are done vary from certification to certification. The one in the bottom is quite interesting. It's a marine certification, marine compostable. Basically, these particular materials, if you drop them into the ocean, if it's essentially biodegrade within the ocean. There are some issues associated with that, and actually, there are some parts of the country that feel that this particular certification promotes littering, particularly in a marine environment. So, you know, people see that it's marine compostable, they just throw it overboard or off their boats or whatever it happens to be. And you end up with a lot of trash where it doesn't need to be. So the main thing that I want people to take away from this is that each of the insignias has its own set of criteria for certification, and it would be a lot better if we maintain a certain set of criteria and you don't have all these competing certifications out there at some point. Let's go to the next slide. So what actually happens with composting? Organic matter is broken down by bacteria and fungi. The ratio of the carbon and nitrogen within the material is really important for the breakdown of the organic matter. You see, I have listed there the 30 to 1 is a good starting place for it. What happens when composting takes place is that the first thing that happens is there's a release of organic acids which drop the pH of the compost. These acids start in and break down lignins and celluloses, particularly with like paper products and things along those lines. The bacteria and fungi typically need 10% oxygen in their atmosphere to function. So they will function without oxygen, but it promotes a different type of breakdown. So, and you see the last point there is that if the compost goes anaerobic, that is, if it's less than 5% oxygen, it'll start producing a lot of odors, and that includes hydrogen sulfide, otherwise known as rotten egg smell. So anyways, that way the industrial composting facilities try and maintain at least 10% oxygen in the atmosphere to function. One thing that I didn't list here is that the necessity of the moisture in the composting as well. That's a very important part of it as well. So what actually happens to the plastics? There are 3 different stages that they go through, and you can see there the picture of the bottle that's biodeteriorated in the background there. The first thing that happens, I guess it is referred to as biodeterioration, and this is the modification of the mechanical, physical, and chemical properties of the plastics. It then goes on to break down further into biofragmentation, and that's where you're converting long chain polymers to shorter chain polymers, otherwise known as oligomers, and monomers by the microorganisms that are doing the breakdown. And the last of these is called assimilation. Microorganisms are supplied the necessary carbon, the necessary energy, nutrient sources, and creating the conversion of the bioplastics into CO2, water, and biomass. And this biomass is the compost that we're all familiar with, that we use on our gardens. So the degradation of the bioplastics, if we're going to get into a little bit of chemistry here, where it degrades, the degradation typically requires enzymatic or catalytic hydrolysis of ester linkages in the biopolymers. Most biopolymers have these ester linkages associated with them. And these ester linkages, which you'll see in the materials that I'm getting ready to talk about, are the keys to their degradation. In soil, bacteria produce enzymes that cause this hydrolysis to occur. If you have it at ambient or room temperatures, the rate of degradation can be quite slow. As you increase the temperature, increase the moisture content, the rate of degradation increases as well. So how do we make these bioplastics? There are a lot of newer ways to make bioplastics out there. One is fermentation. And you see the image of the fermentation facility at Danimer Scientific, which is one of the PHA manufacturers, and that's based where I am here in Kentucky. So these are, it's typically making what are known as PHAs, polyhydroxyalkanoates, and they're made using fermentation methods, which is really nice. It's an easier way of doing this, and a lot of these fermentations can either use sugars derived from corn, sugarcane, or sugar beets. And the thing to note about all that is those are all sustainable sources. Others they can use oils derived from a variety of sources. The Danimer facility uses canola oil here in the US, but other facilities around the world use other oils. And one that's being considered or is on its way is the oil from waste agave, which is the material that comes out after tequila production down in Mexico. The bioplastics are then extracted post-fermentation. So let's get back to the polylactic acid. Polylactic acid generally breaks down, again, through the hydrolyses of these ester linkages that I was talking about previously in the backbone of the monomers. And it breaks down to material called glycolic acid. PLA has significant shortcomings when you try and process it by itself. But when you mix it with other polymers, PLA becomes easier to manipulate, and it has much improved mechanical properties associated with it. What other polymers can you mix it with? PCl, polycaprolactone, PBS, polybutylene succinate, PHB, polyhydroxybutylene, and PBAT, which is probably the one that most people use to mix with the PLA. It's called polybutylene adipate terephthalate. So if we take a look at the chart on the right-hand side of the screen, the two axes there are renewable raw materials versus petrochemical raw materials. And then on the left-hand side, you have non-biodegradable. The right-hand side, you have biodegradable. And each of those quadrants represents a different set of polymers. So, so the first one to take a look at is in the lower left-hand corner, and that's the conventional plastics that are out there. Polyethylene, polypropylene, polyethylene terephthalate. Those are the ones that I was referring to earlier. And again, those are petrochemical-based raw materials, and they are non-biodegradable. So there's another set of polymers that are out there, and that is polyethylene, polypropylene, and polyethylene terephthalate. But these are made of bio-based materials. So they can be made from corn and other types of bio-based materials. So it does make them somewhat more sustainable, but again, they're not biodegradable. If you then go to the bioplastics that are down in the lower right-hand corner, you see those are the ones that I have listed there: PBAT, PBS, PCl. The interesting thing about those is that those are petrochemically based, but they're biodegradable. So it gets a little bit confusing here, but there are some of those, for example, the polycaprolactone, the PCl, and the PBS, where people have now found bio-based routes to those, where they use renewable raw materials and they're biodegradable. So they would be moved up into that upper right-hand quadrant. The upper right-hand quadrant, the bioplastics there, PLA, polylactic acid, PHA, polyhydroxyalkanoates, and then it talks about starch blends there. These are all biodegradable materials, and they're based on renewable raw materials. If you can stay within that quadrant, that's the place to be. If you cannot stay within that quadrant, I think the bioplastics is a better way to go. If you end up with bioplastics in the upper left-hand corner, it typically isn't not a whole lot different from the conventional plastics, but their carbon footprint is significantly reduced by the use of renewable raw materials. So if you look at commercialization of these types of materials, the biodegradable materials within North One that has significant commercial success is what's referred to as mulch film. And mulch film prevents weeds from growing around crops. For example, if you go out to a strawberry field or other fields that have these types of things to prevent the weeds from growing there, a lot of that mulch film that you see there is polyethylene based. So it's still made from polyolefins. However, it's becoming more prevalent that is going to bio-based materials. And the reason for that is that it actually has an economic pull. The bio-based materials overall are cheaper to use than the polyethylene film. So the bio-based materials, instead of having to have the material pulled up at the end of the season, the farmers can just simply disc it under and it biodegrades. If you have the polyethylene film, they have to pull it up and then get rid of that material, which requires significantly more labor, and then you have the disposal costs associated with it as well. So most of these are made through a blown film process where the material is extruded through a circular die, and that's what you see in the lower left-hand corner there. That's a blown film. That one happens to be polyethylene, but materials such as PBAT and PLA mixed together, and others can be blown into films along these same lines. That particular line right there, the material comes out of that annular die, goes up about 3 stories, is collapsed at the top, and then comes back down where it's slit into rolls of material. The vast majority of what you see with regards to the crops, as I stated before, is still polyethylene, but you will see more and more with regards to bio-based materials in the near future. All right, so let's talk about next generation plastics for cannabis packaging. There's a lot of possible uses for bioplastics for cannabis packaging. The main ones that you will see in the near future are injection molded. So the injection molding of boxes and for small and large amounts of cannabis, it's already taking place in some places. So they have injection molding for bottles for extracts, whether it's a THC extract or CBD extract or whatever. This again has a possibility. Using biomaterials as blown film for bags is also a possibility. However, there are issues for the use of bioplastics for these materials. The barrier properties are typically not as good as conventional plastics. That is, they let oxygen and moisture travel through them more quickly than do the polypropylenes and the polyethylenes of the world. The strength typically is not as bite resistant. Child resistant packages typically need to have a bite resistant component associated with them, particularly the bags. So you'll still see conventional materials being used for bags in the cannabis packaging world. And again, we go back to the fact that the infrastructure for composting is not in place in many parts of the country. So this is really a big issue. So even though it's bio-based materials in some cases, the littering that's occurring, all that sort of stuff, it still doesn't promote the breakdown of these particular materials that need to be industrially composted. There are issues with the mixing of biopolymers back into conventional recycling streams. So conventional recycling streams, for example, if you do have polyethylene, polypropylene, polyester, and you end up with PLA, PBAT in it, that's an issue on its own as well. So, if you think about this, using the bioplastics still has a ways to go, unless it's used for something that we in the packaging world refer to as dust covers, where it's basically there to or just to hold the material and not necessarily create a barrier. So here are the questions that we have for the materials going forward. Will North America choose compostable materials over those made from fossil fuels? Well, we've already seen the possibility of fossil fuel-based plastics being marginalized. And it's going to continue to happen. I mean, not to say that it's not a huge market for those materials already, because it is, and you'll be seeing that for a very long time. In Europe, you'll see more compostable materials coming out. For example, in Italy, all of the grocery bags and things along those lines need to be compostable these days, and they have particular indications associated with them, so you know they're compostable. That hasn't happened, and there's no standardization of that within North America just yet. Will North America follow Europe in legislation affecting the plastics industry? Yeah, I think that there will be some of that, but it's going to be a long time. There are parts of the country that really don't see this as a big issue, and they're going to continue with landfills for quite some time. Will industrial composting facilities be built, or will we see a continuation of landfilling? And I think the answer is yes and yes. So I think that you will see more composting facilities built. They're going to be accepting more along the lines of packaging materials and food scraps, but you're going to continue to see landfilling for the foreseeable future. There needs to be infrastructure for all of this. So there needs to be separation of the compostable from the recycled and the landfilled materials. So now we have two streams, and there's going to be three at some point. So, and there already is in some parts of the country. So how will recycling and composting coexist? Well, that's a really, really good question, and we don't really know the answer to that just yet. So what is needed? Education. Education is a huge component of all of this. More education for consumers. The consumers really need to understand what their packaging is made of. They need to understand what's compostable, what's recyclable, how it's going to be recycled, and what needs to go to the landfill. More infrastructure, obviously. We need more composting facility. We need more recycling facilities. But in addition to that, there's going to be innovation needed that's going to be able to take what comes out of those composting facilities and recycling facilities and how it can be utilized to create new products. And as I was saying before, the last of these is that there really needs to be more international standards and definitions. The international standards and definitions are very much a key to all of this. So hopefully I've been able to give you an idea today about these next generation plastics, how they can be used for cannabis packaging, why they degrade, how they degrade, and hopefully we'll be able to head that direction sooner rather than later. Thank you very much. I appreciate it.